Okay, so this is the second video in the series on continuity, and I hope I'll finish the entire continuity part in this video, and so that the next one is about I'm going to start derivatives, I hope, in the next video. So I'm going to do on page 106, I'm going to do problem 29, which asks us to locate the discontinuities of the function and illustrate by graphing. So our function for problem 26 is f of x equals 1 over 1 plus sine x. So this function behaves pretty normally everywhere except for when 1 plus sine x equals to 0, because you can't divide by a 0, or in other words, when sine of x is equal to negative 1. So anywhere sine of x is equal to negative 1, you're going to have this function is going to go to plus infinity. And the reason it's going to go to plus infinity, so every time you have sine of x is equal to negative 1, the function is going to go to plus infinity. And the reason for that is, so sine of x looks something like this. It goes something like this, whatever. That's sine of x. And this is going to be negative 1, and this is 1. So 1 plus sine of x is going to be the same thing, just shifted upwards. So it's going to do something like this. Something like that. So it's always positive, and then it hits 0 every once in a while. And every time it hits 0, you're dividing pretty much by a 0. But because that 1 plus sine of x is always positive, because that the least sine can be is a negative 1. So the least this can be is 0, so it's always greater or equal to 0. When we approach 0, we're always approaching it as a positive small number. So this is always going to be 1 over epsilon, where epsilon is very small but always positive. So because of that, every time we approach 0, we get a discontinuity, or the function is not even defined. But at the same time, the limit, every time we get closer to 0, goes to plus infinity. So the limit is defined. It's not like 1 over x, which goes to plus and minus infinity. So now the question is, let's think about when sine of x is equal to negative 1. So one time that this happens is if sine of 3 pi over 2. But sine it repeats a lot, an infinite amount of times actually. So because it's a repeating function, there are actually an infinite amount of times when it equals 0. And so for any repetition of this, so 3 pi over 2 plus 2 pi n, because that's the period for sine. So every time this happens, we get a negative 1. And we get, so the function is continuous everywhere. Sine of x is continuous everywhere, except for all of these numbers, where it goes to positive infinity and it's not defined. So it's not actually defined for any of these numbers. And as we approach it, we go to positive infinity. Okay, next problem. Okay, I'm not going to do problem 30. I'm also not going to do problem 31 to 34. It's pretty simple. Most of them just require you to plug in the number, I believe. Basically, you claim that the function is continuous using the laws of continuity, and because of that, you can just plug in the number for the function. I mean, I'll do one example quickly. It's example 31. The limit as x goes to 4 of 5 plus the square root of x over the square root of 5 plus x. So because that if you plug in 4 down here you don't get a 0, by the theorem for continuity, and this is continuous, right? We take f of x to equal to 5 plus the square root of x, and g of x is equal to the square root of 5 plus x, and because the g of 4 does not equal to 0, we can basically say that this limit is equal to the limit 5 plus the square root of x for x going to 4 over the limit x goes to 4 of the square root of 5 plus 4. And again, both of these function, sorry. Okay, let's just fix that. This is x and this is x. Both of these functions are continuous because that they're either polynomials or root functions. This is a root function. So because that they're continuous, we can claim that the limit of f of x is just the limit as x approaches a of f of x is equal to f of a. So we can just plug in the 4. So we get this is equal to 5 plus the square root of 4 over the square root of 5 plus 4. So it's very straightforward. The next problem I'm going to do is going to be problem 35. Show that f is continuous on the interval negative infinity to infinity, and we have f of x equals x squared if x is less than 1, and it's equal to the square root of x if x is greater or equal to 1. So first, when x is not close to 1, meaning in the interval, so let's first look at the interval negative infinity to 1, not including 1. Well, on this interval, f of x is basically just defined as x squared. X squared is polynomial, so it's continuous on this interval. Then also, similarly from the interval 1 to infinity, f of x over here is defined as the square root of x, and so again it is a continuous function because that it is a root function, or what do they call it? Yeah, root function. So that's simple. So the question is it continuous at 1? So for a equals 1, is this continuous? And hopefully it is. So let's look at the limit as x approaches 1 from the left of f of x. Well, this is the limit as x approaches 1 from the left of x squared, right? Because that x is smaller than 1 when we approach from the left. And this is equal to 1. And similarly, the limit as x approaches 1 from the right of f of x is equal to the limit as x approaches 1, as x approaches 1 from the right of the square root of x is equal to 1. And so we know that the limit as x approaches 1 of f of x is equal to 1. And at the same time, f of 1 is equal to the square root of 1, which is equal to 1. So this is equal to f of 1, right, which is equal to 1. Because of this, the definition of continuity is satisfied, right? F of x is equal to f of a, because a is 1. The definition for continuity is satisfied, and we just proved, or we showed that f of x is continuous. Looking at the next problem, we want to show that f of x defined as sine of x if x is if x is less than 4 pi over 4, and cosine of x if x is greater or equal to pi over 4, right? So the limit as x approaches pi over 4 from the left of f of x is equal to the limit as x approaches pi over 4 from the left of sine x, which is equal to sine of pi over 4 and this follows from the fact that sine is continuous, so we can just plug in the number for the limit, and this is equal to the square root of 2 over 2. And the limit as x approaches pi over 4 from the right of f of x is equal to the limit as x approaches pi over 4 from the right of cosine x is equal to cosine pi over 4 is equal to the square root of 2 over 2. And f of pi over 4 is equal to cosine of pi over 4, because this is x is greater or equal, is equal to the square root of 2 over 2. So because of this, the limit as x approaches pi over 4 of f of x is equal to the square root of 2 over 2, which is equal to f of pi over 4, and that completes the problem. So now the next problem I'm going to focus on is problem 37. Find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right, from the left, or neither? Sketch the graph. So I'm actually only going to do one of them, and it is going to be problem 39. Actually, it's better, I'm going to do two of them, problem 38 and problem 39. So problem 38 is f of x is equal to x plus 1 if x is less than or equal to 1, and it's equal to 1 over x if x is between 1 and 3, and it's equal to the square root of x minus 3 if x is greater or equal to 3. Okay, so let's first look. So the limit as x approaches 1 from the left is going to be, we're dealing with this one, so we're going to have x plus 1, and this is going to equal to 2. And then the same limit as x approaches 1 from the right. So now we're over here. We're using 1 over x, so this is for 1 over x is going to be 1, and f of 1 is also going to be 2. So already we can kind of start graphing this. X plus 1 is a line which intersects the y axis at 1. It goes up to 2, right? And at 2 it's going to be 2, and this is for 1 right over there. But then when we approach from the right, we are at 1. So here's 1. So we're at 1, and we're dealing with 1 over x, which would look something like that. I did not make enough room for this graph. Okay, but this is how it looks for now, and we're going to go to another page eventually and draw the whole thing. So So now the second part is the limit as x goes to 3 from the left is, we're dealing with 1 over x. This is going to be a third. The limit as x goes to 3 from the right is now x minus 3, and this is going to be 0, and f of 3 is going to also be 0, because again, for x equals 3, we're dealing with the square root of x minus 3. So now we can draw this. So again, we're dealing with a line that intersects the y-axis at 1, goes up to 2, is still there at 2, then jumps down to 1, goes from 1 until 3, so this is 1, this is 3, goes from 1 until 3, stops at 3, jumps down to 3, and then becomes the, so the normal square root of x looks something like this. So when we have the square root of x minus 3, we're basically shifting right by 3, and then we're doing exactly what the square root of x does. So it's going to go something like that. And that's our graph. Very cool. Okay. Next problem we're going to do is problem 39. So we have f of x. We have f of x is equal, okay, to x plus 2 if x is less than 0, to 2x squared if x is between 0, x, and 1, and 2 minus x if x is greater than 1. Okay, so now let's again look at the limit as x approaches 0 from the left. From the left, x is smaller than 0. So this is for x plus 2, and this is going to be 2. And then the limit as x approaches 0 from the right is going to be, this is for 2x squared, because now x is greater than 0. And this is going to be 0. And then f of 0 is also going to be 0. F of 0 is equal to 0, because this is for equal. Then the limit as x approaches 1 from the left is again, so this is for 2x squared, is going to equal to 2. And the limit as x approaches 1 from the right is going to be over here, because now x is greater than 1, so it's going to be 2 minus x, and this is going to be 1, and f of 1 is equal to 2, 1 squared is equal to 2. So, yeah. And everywhere else, everything is continuous with the same exact claim. For this problem, everywhere else, aside from 3 and 1, everything else is continuous, because each one of these is continuous on its own. So everywhere else we're continuous except for 0 and 1, where we have discontinuities, as we saw. So if we graph this, we have x plus 2 is a line which intersects so this is 2 and intersects 2, but it's not filled at 2 because it's not continuous from the left. Then it jumps down to 0, and it is filled in at 0, and at 0 it's 2x squared, which would look something like that, because that, well, x squared looks something like that, and 2x squared just makes it sharper, so we're just going to draw like that. And this comes back to 2, right? Because as we reach 1 from the left, we're back at 2, and here we are filling it in, so it is continuous from the right at 0 and from the left at 1, but it's not continuous from the right at 1 because that now it drops. So this is a line going like that. It drops to 1. So here's 1, drops to 1, and then it just becomes a line. That's problem 39. So let's do problem. Okay, so the next problem we're going to do is so the gravitational force exerted by the Earth on a unit mass at a distance r from the center of the planet is F of r is going to equal to Gm little r over r big R to the third if r is bigger than big R, and it's going to be Gm over r squared if r little r, sorry, this is little r is less than big R, and this is little r is greater or equal to big R. And the question is, so where m is the mass of the Earth, r is its radius, and g is the gravitational constant. So the question is f a continuous function of r? So we want to see whether the limit as x goes the problem, so this is a continuous function and this is a continuous function. The problem might occur, the discontinuity might occur when r equals big R. So the limit as r goes towards big R of f of r, and we want to see that this is the same as f of r. So this limit, we have to split it up because the function is different. So from the left of f of r is equal, so now r is smaller than big R, so it's equal to Gm r over r to the third. This is the limit, so r goes towards r from the left, and this is the same as Gm r over r to the third, or same as Gm r squared. Going from the right, for f of r is equal to the limit r going to big R from the right of Gm r squared, which is the same as Gm r squared. So the limit exists. Now f of r, we're just going to use this one, is just going to be Gm r squared. So f of big R is this, which is equal to the limit, and so this function is continuous. It's equal to the limit, so the function is continuous. Very nice. Now we're going to do problem 41. So we have a function f of x is equal to cx squared plus 2x if x is smaller than 2, and x cubed minus cx if x is greater or equal to 2. So we want to find the c that makes this function continuous everywhere. So the way to do this is we want the limit over here, this function, to equal, as we approach 2, to equal f of 2, to equal the limit as we approach from the right, but one simple way of doing all this, okay, so we can just say the limit as x approaches 2 from the left of f of x is just equal to c4 plus 4. Just plug in the 2's over here. That's not a 4 actually. This is, oh no, that is a 4. 4. And we want this to equal f of 2, which happens when we just plug in 2 over here. So that will be 8 minus c2. So in other words, we want 4c plus 4 to equal 2c minus 8, or we want 4c minus 2c to equal negative 12, or we want 2c to equal negative 6, or we want c to equal negative 3. Negative 3. I think, yeah, there was a mistake done here, because that and that are not the same. Okay, let's try this one again. So this is the same as 4c plus 4 is equal to negative 2c plus 8, or in other words, we want 6c to equal 4, or c to equal 4 over 6, which is equal to 2 over 3. So that's what we want c to equal. So when c is equal to 2 over 3, we will have that the limit as x approaches 2 both from the right and from the left of f of x is just going to be f of 2. And we're going to have continuity because we checked this. We did that over here. We just made them equal to each other. We get to plug in the points for the limit just because of this function is continuous and this function is continuous. We don't even have to look at this as we approach from the right. We can just plug in the 2 for x equals 2, make sure that they're the same, and because of this is continuous, if it's continuous at 2, it's going to be continuous for x bigger than 2, and so we're done. Yeah, okay. The next problem is interesting. So I will do it. Problem 42. So problem 42 asks us to find an A and a B that makes the following f continuous. So we have f of x equals x squared minus 4 over x minus 2, and this is if x is less than 2. Then it's equal to ax squared minus bx plus 3 if x is between 2 and 3, and then it is 2x minus a plus b if x is greater or equal to 3. So we want them to be equal. So well, the one problem we might have, okay, one problem we might have is, well, we are not told what happens when x equals to 2 in the book at least, so I'm just gonna do that to make this work, because otherwise we would not know what x actually is at 2. And obviously it has to be here. It can't be over here because you cannot have x being equal to 2. That wouldn't be good. Anyways, mistake in the book, whatever. Okay, so we want the limit as x approaches 2 from the left, which is for x squared minus 4 over x minus 2. We want this to equal to, now we're going to plug into a, so a times 4 minus b times 2 plus 3. This is one thing that we want. And another thing that we want, because this is continuous and this is continuous, everywhere we can just plug in 3. So another thing that we want is for a 3 squared minus b 3 plus 3 to just equal, straight out, plugging everything in, 2 times 3 minus a plus b. That's another thing that we want. First, let's look at this. What's the limit over here? So this is the same as the limit as x approaches 2 from the left of x minus 2 x plus 2 over x minus 2, right? Because x minus 2 times x plus 2 is equal to x squared minus 4. Okay, so now these cancel. You plug in a 2 and this becomes 4, right? So we want this to equal to 4. Okay, so what are the two conditions that we have? So we have 4a minus 2b plus 3. So 4a minus 2b plus 3, that to equal to 4. And 9a minus 3b, so 9a minus 3b plus 3 to equal to 6 minus ab. 6 minus a plus b. Or in other words, looking at the second condition, what we want is 10a minus 4b to equal to 3. Okay, so now we can also say that we want, okay, and over here, get rid of the 3, so this is going to be equals to 1. So we want 5a minus, we can divide all of this whole thing by 2, so 5a minus, by negative 2, let's divide by negative 2, yeah, so this is going to be negative a plus 2b equals to negative 1.5. Now we can add this to this side and this to this side, right, because they're equal. So adding this to this side is going to get us 4a minus 2b plus minus, so minus 5a plus 2b is equal to 1 minus 0.5, so it's going to give us negative 0.5. Or in other words, okay, so these b's cancel, so you're going to get 4a minus 5a, so we're going to get minus a is equal to minus 0.5, or a is equal to a half. Okay, basically there are a bunch of ways to solve a set of equations with a's and b's. I hope you know how to do it. One way is to put the equations in such a form that when you add this equation to this side and this part to that side, the b's, for example, cancel, or the a's cancel. Another way would have been to solve for b and then plug it into here in terms of a, because you just want the equations in terms of one of the variables. Now that we know what a is, we can just plug it in, for example, here, and we get 4a, which is 2, minus 2b is equal to 1, or negative 2b is equal to negative 1, or b is equal to a half 2. So for a equals a half, b equals a half, that this function f of x is continuous, because that the limit over here is going to be equal to what happens when we just plug 3 into here. So we're going to get the limit of f of x for basically everything will work out, and we're going to get the limit for as x goes to, what was it, 2? Yeah, as x, problem was that this is problem, okay, this is problem 42. So as x goes to 2, as x goes to 2 of f of x is equal to f of 2. We get this because we solved for a and b to make sure that that happens, and we're going to get the limit as x goes to 3 of f of x is equal to f of 3. That was an interesting problem. So the next problem we're going to do, okay, so I'm going to skip problem 44, 43, 44, and 45, because essentially, again, a lot of them is just finding limits. Actually, 44 is not, it's going to the intermediate value theorem. But I am not going to do it because I'm going to just do 46, which is also dealing with the intermediate value theorem. I'm doing problem 46, which says suppose f is continuous on the interval 1, 5, and the only solutions to the equation f of x equals 6. The solutions are x equals 1 and x equals 4. And we know, so if f of 2 is equal to 8, prove or explain why f of 3 must be greater than 6. So first, let's just write down the intermediate value theorem, which states, this is on page 104, if f is continuous on a closed interval ab, so we have a closed interval ab, and we have a continuous function f on it, and let n be any number between f of a and f of b, where f of a does not equal f of b. So basically you have, let's say, a and b, and a maps over here, this is f of a, and b maps over here, this is f of b, and let n be any number in between them. So this is where a maps and this is where b maps. Then there exists a number c inside ab, so there's a number c in here, let's say c, such that f of c, such that n is equal to f of c. The reason is because that, okay, so this maps right over here, so the function starts over here and it ends over here. And no matter how you draw this function, if it's continuous, then there will always be a point right over here that's going to be c. So you can also use this, for example, if you have a function which you find at some point it's negative and at some point it's positive, and this function is continuous, then you know that at some point it must be 0. So there will be a c such that f of c equals 0. So for us, we know, okay, we know that the only solutions for, so here's my function, and we know that the only solutions for the function of f of x equals 6, so this is 6. So the only times that f of x is equal to 6 is at the point x equals 1 and x equals 4. Yeah? But we also know that f of 2, for 2, f is greater than 6, meaning it's 8. Now, let's suppose that f of 3 is smaller than 6. Let's suppose that f of 3 is here. Then in order to get here, the function would have to go to 2, where it's 8 at 2, right? Okay, I'm going to draw these numbers a little better. So this is 6, and then this is 8. So the function would have to go to, okay, this is how the function does look. But let's imagine the function really goes down here. So the function would have to go to 8. Okay, this is 8. And then go down, but over here it would hit 6. You can't jump over 6. If it's going to go to a number less than 6, right? If f of 3 is less than 6, let's suppose it's less than 6. Well, then at some point it has to dip below 6 because it's above 6 at 8, right? And it's then below 6 suddenly at 3. So before 6, between 2 and 3, it's going to have to hit 6. But then there will be 3 places where the equation f of x equals 6 is satisfied, right? Because you're going to have x equals 1, x equals 2, and then you're going to have, for some c, between 2 and 3, so c is greater than 2 unless c is greater than 2, and, well, let's not call it c because that's confusing with the equality. W is greater than 2 and less than 3, right? We're going to have a w such that f of w equals 6. That w can't be 4. The w can't be 1 because it's between 2 and 3. Because for 2, we're above, we're at 8. And suddenly for 3, we're below. So the w has to be between 2 and 3, and that is impossible. Okay, I'm going to do 2 problems in the intermediate value theorem, and then quickly move away, or 2 or 3, whatever, because again, we're running out of time, and I don't want another video on continuity, although I can go above an hour, so that doesn't really matter. Okay, so we have, let's look at problem 47. We want to, it's saying use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So x4 to the 4th plus x minus 3 equals 0 in the interval 1 and 2. So, right, this is what f of x equals, and we want to show that there's a solution to this equation. Okay, this is not going well. X to the 4th power f of x. We want to show that there's a solution to this equation. So let's look at f of 1 and at f of 2. So f of 1 is equal to 1 plus 1 minus 3, or minus 1. And f of 2 is equal to, what is it? I don't know, 16? 16 plus 2, which is 18. So 18 minus 3, which is equal to 15. So if you look at our f, right, at 1, here's 1, it's negative 1. It's less than 0. And suddenly at 2, it's 15. That's 15, let's say. The only way for this to happen is if it's somehow, at some point, this is at 2, that's not 2, here, 2. At some point it goes and it hits the x-axis. That, over here, will satisfy f of x equals 0, meaning it's going to be a root, right? F of x just hits 0. So because of that, we just proved that this has a root, or that this equality equals 0 can be satisfied by some c, because we can say that, listen, there's a w greater than 1 and less than 2 such that f of w is equal to 0. And to be specific, when using the intermediate value theorem, we're going to say, listen, we have a f of a, which is equal to 0.1, and this is a is 1, and an f of b, which is equal to 15. So for any number between them, for any n between them, we will have f of some c equals to that number, n. But 0 is between -1 and 15, so we can take n equals 0. So again, we're going to have f of omega, or f of c, equals n, which is equal to 0, and that's how we solve that problem. Let's look at problem let's look at problem 49, which says, so we want to show that there's a point where cosine of x is equal to x, right? That's what we're trying to show, that there is a point that gives us the equation in the interval 0, 1. So this is the same as asking, well, is there a point of cosine x minus x is equal to 0? So let's put in 0, and we're going to get 1 minus 0, which is equal to 1, right? So f of 0, let's take f of x is equal to cosine of x minus x. So f of 0 is equal to 1 minus 0 is equal to 1. Now f of 1 is equal to cosine of 1. Cosine of 1, which I put in the calculator, is like 0.54. I mean, what is it, like this square root of 2, or 2 divided by the square root of 2? No, I don't think so. No, that's not it. Anyway, maybe square root of 2 divided by 2. See, I think so either. No, it's not going to be that either. Anyway, but this is going to be 0.54 minus 1, which is equal to some negative number. 0.54 minus 1 is negative 0.46. So we have, again in our function, we have that at 0 we're positive. So at 0 we're positive, and at 1 we are negative. We're 0.46. So again, take f of a to equal f of 0 to equal 1, and f of b to equal f of 1 to equal negative 0.46. By the intermediate value theorem, we're going to have that there will be a c such that f of c equals 0, because this is positive, this is negative, or in other words, we're going from here down to here, and there should be a point where we hit the 0 at the x-axis. So because of that, we can claim that there exists a c such that f of c equals 0, or we can claim that cosine of c minus c is equal to 0, or that cosine of c is equal to c, which is exactly what we wanted. We want to show that there is a c such that is satisfied. Okay, next problem. Let's just do one more intermediate value theorem problem. I'm definitely going to go over an hour. Whatever. So we're going to have, so we want to show, so this is x, and that's 3. It's equal to 1 minus x in the interval 0, 1. So we want to show that there exists an x which satisfies this equation in this interval. So let's make f of x equal to x3 minus 1 plus x and equal to 0, right? We want to show that f of x is sometimes equal to 0. So what is f of 0? F of 0 is 0 minus 1 plus 0, so it's minus 1. And f of 1 is equal to 1 minus 1 plus 1, which is 1. So again, by the intermediate value theorem, there's a number. So this is f of a equals f of 0 equals negative 1. F of b equals f of 1 equals 1. So there's a number between them, 0. We can choose 0 to be the number between them. So we know that f of c for some c is going to be equal to 0. So we know that for some c we have c3 negative 1 plus c is equal to 0, or in other words, c that is equal to 1 minus c. So because of this, we know that there is some number between the 0 and 1 which satisfies that equation. Okay, the next problem to do is problem 55. Prove that f is continuous at a if and only if we have that the limit as h goes to 0 of f of a plus h is equal to f of a. Well, we know, so we have the definition of continuity that the limit as x goes to 0 of f of x is equal to, not 0 to a, sorry, is equal to f of a, right? We can take, that's x going to 0, we can take, sorry, this is h plus h. We can take our x, we can take our x to be a plus h, sorry, a plus h, and where h is going to 0, where h is going to 0. And in this case, if we take x to be a plus h where a is going to 0, we have that x is going to a. So we have this part. So this is that. So now what we're saying is that we want, so now by this claim we get that the limit as x, sorry, the limit as x goes to, so x, we can change what x is as, sorry, a plus h, it's not an h, a plus h goes to a of f of a plus h is equal to f of a. This is over here just replacing, every time you see an x, replacing it by a plus h. But this is an equivalent statement to saying, right, if a plus h is going to a, all we really want, right, we can like take a negative from both sides, kind of, a negative a. All we really want is limit as h goes to 0, right, because that will satisfy a plus h going to a if h is just going to 0 of f of a plus h, and that must be f of a. So, yeah, I guess that's kind of how we do that proof. So the next problem I'm going to do is problem 59, which is for what values of x is the function f continuous, where f of x is equal to 0 if x is rational, and 1 if x is irrational. And the answer to this is that the function is not continuous at any point, right? Let's imagine let's imagine. Okay, we showed in the previous video that the limit of as x goes to 0 of f of x for this x does not exist. Now, by the same account, we can show that for any a, for any single number in the interval, the limit as x goes to that a of f of x does not exist. Going through the same exact argument that we did in the previous video, and because of that, but we know that that f of a is either 0 or 1, depending on whether a is rational or irrational. But the limit over here doesn't exist. And so because of that, we cannot say that f is continuous anywhere, which makes sense. There are a lot of, well, you can say the following. The rational numbers, the irrational numbers are more in cardinality, whatever that means. It's a bigger infinity than the rational numbers. But the rational numbers are dense in the real numbers, which basically means that for any irrational number that you give me, I don't know, square root of 2, pi, and so on, you can find a sequence of rational numbers. So let's say the number you give me is square root of 2. You can find a sequence of rational numbers that approach that point, the square root of 2. So every single rational number and irrational number have a bunch of the other kind. You know, if it's a rational number, they have a bunch of irrational numbers around it. And if it's an irrational number, they have a bunch of rational numbers around it. And because of that, as we approach any single number, it might be rational or irrational, there will always be an infinite amount of numbers which f of those numbers is different than the number that we're approaching. Meaning, so let's say we're approaching a irrational number. So here, let's say we have an irrational number, and we're approaching it. So f of that irrational number, right, f of a, is going to be 1. But there will be so it's going to be 1. But there are going to be an infinite amount of points close to it, which f of those points is 0. So you cannot say that the limit, we cannot say that the limit as x approaches a is going to be 1, because there will be a bunch of numbers that their limit will be that will be 0. Okay. So now for the next question, the question asks for what x is the function g continuous, where g of x is defined as 0 for x rational and x for x irrational. Well, so for any point where x is different from 0, right, where these two claims are different, again, by the same exact argument that we made before, we will not have a limit. But, well, as we approach 0, so as we approach 0, as we get closer and closer to 0, all the irrational numbers that we're dealing with, f of them is going to also get pretty close to 0, right? Because the function is going to look something like this. If we're dealing with x, it's going to look something like this. All the irrational numbers are going to map like that, and the rational numbers are mapping just on a line. These are rational numbers where they map, and the irrational numbers map over here. As we approach 0, they agree. So the limit, so for x equals 0, we're going to have that the limit as x approaches 0, even though a lot of these x's might be irrational numbers, still the limit of this is going to be equal to x, which is going to be equal to 0, simply because, which is equal to f of 0, because 0 is a rational number, simply because that a bunch of the irrational numbers are just going to, they're getting really, really small, the irrational numbers, and so this is going to get really small, and it's pretty much going to hit 0. But the function, while continuous at 0, is not continuous anywhere else. Okay, let's look at problem 61, which asks, is there a number that is exactly 1 more than its cube? Right, we want a number such that x is equal to x cubed plus 1, right? That's what we're asking. Or in other words, using the intermediate value theorem type of stuff, what we want is a number such that x cubed plus minus x plus 1 is equal to 0. And we'll set this to f of x, right? This is exactly what we're looking for. And I do believe, no, we did not do this exact one. So let's take f of 1 is going to equal to 1 minus 1 plus 1, which is 1. And let's take f of negative 1, which is equal to negative 1 minus 1 plus 1, which is equal to negative 1. Because of this, we can say that there's a c, again using the intermediate value theorem, f of c equals 0, right, in the interval 1, negative 1, right? And so we have that for the c cubed minus c plus 1 is equal to 0. Or, in other words, for this c, we have c is equal to c to the third plus 1. Sorry, I believe I made a mistake. Yeah, because this is going to be minus, which is plus, and this is still going to be plus 1. Right? Yeah. So no, we need to choose. So this one is okay, but for the other one, okay, let's choose 2 for the other one. So what is f of negative 2? Well, this is negative, what is it? Negative 8 minus plus 2 minus plus 1, which is going to be negative 5. Okay, so now, so again, f of a equals f of 1 equals 1, and f of b equals f of negative 2 is equal to negative 5. So we have, by the intermediate value theorem, right, again, this function is basically negative at negative 2, right, at negative 2 it's negative, and then a positive 1 it's positive, so it's going to go like this. So there must be a point c such that f of c equals 0, or in other words, c cubed minus c plus 1 equals 0, or c is equal to c cubed plus 1. So yeah, there is a number that is exactly 1 more than its cube. Okay, I'm skipping the next problem. I'm going to do problem 63, which says, show that the function f of x equals x to the 4th sine of 1 over x if x does not equal 0, and 0 if x equals 0. Show that this function is continuous on the interval negative infinity to infinity. Well, when x is not 0, x to the 4th is continuous, sine 1 over x is continuous, and so sine of 1 over x is continuous, all following by all the rules of continuity that we did, right? This is a polynomial, this is also polynomial or something, and then this, so sine is continuous, right? So we would take f of x equals 1 over x, and g of x equals sine of x, and so this is going to be g of f of x, which is also continuous because that f is continuous and g is continuous, right? All the rules that we did before. So, okay, so now we need to show that the limit as x goes to 0 of f of x is equal to f of 0, or in other words, to f at 0, when x is 0, this is just 0. Well, we know that sine of 1 over x is bounded by -1 and by 1, right? Basically, we're going to try to squeeze x to the fourth to find its limit, which we did before. So this is bounded by x to the fourth sine 1 over x is less than x to the fourth, right? So the limit as x goes to 0, negative x to the fourth is equal to the limit as x goes to 0 of, sorry, this is going to have x to the fourth, of x to the fourth sine 1 over x is equal to the limit as x goes to 0 of x to the fourth is equal to 0, right? Basically, squeeze theorem. So now we have that the limit as x goes to 0 of f of x is equal to 0, because when x is going to 0 but not 0, we're basically going to use x to the fourth sine x 1 over x, which is 0, and this is equal to f of 0, and this completes that claim. So the next problem we're going to problem 64, which A says show that the function f of x equals the absolute value of x is continuous. Well, when x is not equal to 0, this function is very simple. It's basically negative x over here, and then it's positive x over here. So the real question is, it's 0. What is it, right? Because we're going to have, so by definition, f of x is going to equal x if x is greater or equal to 0, and negative x if x is less than 0. Well, so the limit as x approaches 0 of f of x from either side is very clear to see. It's 0, which is equal to f at 0, so that's done. And then part B says prove that f as a function is continuous on an interval, then so is the absolute value of f. So we want to show that if f of x, whatever it might be, is continuous, then the absolute value of f of x is continuous. And that's pretty simple to see why. F will go like this. Every time it hits the 0, the x-axis, and it might want to go below, it's just going to flip, become negative, and then just keep going. So it's just going to basically go like that. So the problems will never occur for the normal function of f, right? Or for negative f. If f is continuous, the negative f is also continuous. The problems might occur at the points where we go from positive f to negative f, right? From positive f to negative f. Because that f generally, let's say f did something like this, and then it went like here, and then it went here, and then it went here. So these are just the taking like the mirror images of these and projecting them above the x-axis. Well, but over here we're not going to have any problems, because we'll take the limit from this side and the limits from this side, and we'll take the point, and it will be the same. Basically exactly what we did with the absolute value of x can be done for any f. So for part C, the question is the converse of the statement in part B also true? In other words, if the absolute value of f is continuous, does it follow that f itself is continuous? If so, prove it. If not, find a counterexample. Well, it's pretty easy to find a counterexample. you can take f to equal the function -1 for, I don't know, x greater or equal to 0, or 1 for x less than 0, and the absolute value of f is always, no, this is not going to work. Sorry. Okay, this is going to work. Yeah, now. So the absolute value of f is always going to be 1, right? Because if x is greater, if x, yeah, either one of those would have worked, right? Yeah, either one of them would work. This would also work. If x is greater than 0, then the function, the f would look like this. So f is less than 0 is here, and f is greater than 0 is here. But for the absolute value, it would take all of these and just put them here. So it would be continuous for the absolute value, but clearly not continuous for f. So the converse is not true. So last problem, it's an interesting problem. A Tibetan monk leaves the monastery at 7 a.m. and takes his usual path to the top of the mountain. Yeah, okay, so here is 7 a.m. And this is in terms of time, and this is in terms of height. So the monk leaves the monastery and starts going up the mountain and gets to the top of the mountain, arriving at 7 p.m. The following morning, he starts at 7 a.m. at the top and takes the same path back, arriving at the monastery at 7 p.m. So he starts over here, and he takes, so this is in terms of height, I guess, of how high how high the monk is, or where on the path the monk is. But let's assume that, like, if you're a certain height, if you're 10 feet, then you're also at the same exact place. Anyways, this is, let's say, the path, where you are on the path. Fine? Okay, so it's where you are on the path. Like, we would take the path, so here would be the mountain, and there would be a path, let's say like that, and we would basically take the path here and here and kind of pull it, like stretch it, so we get just a line representing where you are in the path. Okay? Something like that. Fine. So now, the monk leaves the monastery on the top at 7 a.m. In the following morning. So the monk is now here, and he leaves, and he goes back down at 7 p.m. He's back down at the bottom. So this point and this point are the same point on the mountain, meaning you're standing on the top of the mountain. Here you are on the top of the mountain. Here you are at the bottom. So this point is this point, and this point is this point, right? And then there are different points in between. So, right, you start at the bottom, you go to the top, and then the following day you start at the top and you go to the bottom. And show by the intermediate value theorem that there is a point in the path where the monk will cross exactly at the same time of day on both days. So as you can see, for us the point is here, meaning there's a point that at this time in the day, whatever this time might be, I don't know, let's say 3 p.m., at this time of the day, the monk was at the exact same point in the path. And you can draw this however you want, right? You start over here, you go up, then following day, you're back over here, right? Because you start at the same time. This is time. And you go down. And no matter how you do this, there will always be a point where these 2 points intersect. And that point will be a point such that you're at the same place in the mountain at that time in the day. Right? So in order to prove this rigorously, you can take h of x to be f of x minus g of x, where f of x is this function over here, the function of, or how the monk went up, and g of x is the function of how the monk went down, right? Function of time, right? Place on the mountain in terms of time, right? Place on the mountain in terms of time. And, well, clearly there's a point, right, at 7 a.m. F of x is much smaller than g of x, so this is going to be negative. This is going to be less than 0. And there's another point, right, so we're going to have f of a, where a is, let's say, 7 a.m., minus g of a is less than 0. And there will be another point, this point right over here, where f of a minus b minus g of b is greater than 0, because over here f of x is much bigger than g of x. G of x is 0, f of x is the height of the mountain. So because of that, you can say, by the intermediate value theorem, that there's some c such that h of c is equal to 0. Or in other words, there's a c such that f of c is minus g of c is equal to 0, or f of c is equal to g of c. So there's a time where you're at the same exact place on the mountain given a c. C is a time. You plug in the c and you find out that you're in the same place in the mountain for both days. And it's pretty clear, like no matter how you draw these, you'll have to intersect, right? You can use something crazy, right? So one day you go like that, and the next day you can do something crazy, I don't know, like that, trying to avoid, but if you want to end up in the bottom, eventually you have to cross, and right there you crossed, and that's where this is C. This is C, and this is f of c equals g of c. Okay, that finishes what we needed to do with continuity. And in the next video, I'm going to start derivatives, definitions for derivatives, and going to chapter